Hello, welcome back. In this video, we'll discuss the Stefan Boltzmann's law, the Wien's law, and the Rayleigh Jeans law. These three laws are important with regard to the blackbody radiation. These laws are empirical in nature and they are basically derived from the blackbody spectrum. We shall first look at the Stefan Boltzmann's law. The Stefan Boltzmann's law connects the intensity of the blackbody radiation with the temperature of the blackbody. It relates the intensity of the blackbody radiation with the temperature of the blackbody. It was first of all empirically studied by Stefan. Later on, it was supported by a theoretical model given by Boltzmann. It essentially connects the intensity of blackbody radiation with the temperature of the blackbody. The law states that the total radiation emitted from a blackbody at a temperature T is proportional to the fourth power of the absolute temperature of the body. The total radiation emitted from a blackbody at temperature T is proportional to the fourth power of the absolute temperature of the body. Here, when we say body, it means the blackbody. Since the emitted radiation is proportional to the fourth power of the temperature of the body, this law also is called as T power 4 law. We write the emitted radiation E as proportional to T power 4, and this gives E is equal to some constant sigma times T power 4, where the constant sigma is called as Stefan's constant. Its value numerically equal to sigma is equal to 5.67 into 10 power minus 8 watts per meter square Kelvin to the power 4. Now we shall discuss the Wien's law. The Wien's law connects the temperature of the blackbody with the lambda maximum, or it connects the temperature with the wavelength for which the intensity of radiation is maximum. To understand the Wien's law, let us look at the blackbody radiation spectrum. Please recollect that this is the blackbody spectrum. In this, we have different curves. Each of the curves, they represent the blackbody spectrum recorded at a particular temperature. For example, the lowermost curve represents the blackbody spectrum when the blackbody is maintained at 2000 Kelvin. The second curve represents the blackbody spectrum when the blackbody is maintained at 3000 Kelvin. Similarly, the third curve represents the blackbody spectrum when the blackbody is maintained at 4000 Kelvin, and the fourth curve represents the blackbody spectrum when the blackbody is maintained at 5000 Kelvin. In all these curves, one can observe that the maximum radiation intensity is occurring for one particular wavelength. For example, for the lowermost curve, that is when the blackbody is maintained at 2000 Kelvin, we have the lambda maximum here. The lambda maximum is the wavelength for which the intensity of radiation is maximum in that particular curve. Similarly, for 3000 Kelvin, the lambda maximum we have here. For 4000 Kelvin, we have here. The lambda maximum for 5000 Kelvin we have here. So as the temperature is increased, we notice that the lambda maximum is shifting towards the shorter wavelengths or higher frequencies. Hence, this law is also called as Wien's displacement law. And this law states that the product of the lambda m times T is a constant which is represented with a C0 whose value is 2.8978 into 10 power minus 3 meter Kelvin. Now we shall look at the statement of the Wien's law. Wien's law states that the peak wavelength lambda max at which the maximum emission occurs for any given temperature is inversely proportional to the absolute temperature of the body. So it states that the peak wavelength lambda max at which the maximum emission occurs for any given temperature is inversely proportional to the absolute temperature of the body. We write this as lambda max is equal to 2.8978 into 10 power minus 3 upon temperature T meters. Now we shall discuss the Rayleigh Jeans law and the ultraviolet catastrophe. They have used generally accepted model of the blackbody, which states that the blackbody is made up of huge number of atoms, and these atoms, they are regarded as small harmonic oscillators. So it is a theoretical model. The generally accepted model was that a blackbody was made up of a huge number of atoms, and the atoms are regarded as small harmonic oscillators. When the temperature of the black body is increased, these harmonic oscillators, they oscillate within the walls of the black body cavity, and during the process of their oscillations, they emit electromagnetic waves, and these electromagnetic waves are expected to establish a standing wave pattern within the cavity of the black body. Please remember that the black body has a cavity like this. When the temperature of the black body is increased, the atoms on the inner surface of the black body, they undergo harmonic oscillations, and these harmonic oscillations will emit electromagnetic waves, and those electromagnetic waves, they move back and forth within the cavity of the black body. As a result, they established a number of standing wave patterns within the cavity of the black body. After attaining the thermal equilibrium, the radiation will emerge from the black body, and thus emitted radiation we call as black body radiation. The Rayleigh-Jeans law uses the Boltzmann's principle of equipartition of energy, which states that the energy associated with the harmonic oscillator, which is equal to kT, where K is the Boltzmann's constant and T is the temperature in Kelvin. Please recall that the black body is a good absorber of radiation and also an emitter of radiation when it is heated. The Rayleigh-Jeans law is E nu, which is equal to 8 pi nu square kT upon C cube, where K is Boltzmann's constant, nu is the frequency of oscillation, C is speed of light, T is temperature in Kelvin. Using this, if you calculate the energy density of the black body radiation, then one can make two observations. The first observation is the energy density calculated is in good agreement with the experimental result, that is the black body radiation spectrum recorded at that particular temperature in the IR region. In the infrared region, the Rayleigh-Jeans law is in good agreement with the experimental results. However, this law predicts infinite energy density in the UV region. But from the experimental result, we know that in the UV region, the component of radiation intensity is small for all temperatures. In fact, for some temperatures, the UV component is 0 also. For instance, when the black body is maintained at 2000 Kelvin, we find that the intensity of UV in the radiation spectrum is 0. Similarly, at higher temperatures also, one can notice that the component of the UV radiation intensity is small in all black body spectra. Therefore, we can say that this law fails to explain infinitely large energy density in the UV region, which is contradicting to the experimental values. And this contradiction is known as ultraviolet catastrophe. The energy density calculated with the Rayleigh-Jeans law agrees well with the experimental results at longer wavelengths of the spectrum, but goes towards infinity at the shorter wavelengths or the UV region. This law predicts that the radiation in the UV region to be infinitely large, while the experimental results show that radiation intensity in the UV region is small. This is a contradiction, and this contradiction is known as ultraviolet catastrophe. This law hints at the shortcomings of classical theories. In this video, we have started by stating that the Stefan Boltzmann's law, Wien's law, and the Rayleigh-Jeans law are empirical in nature. We have given the statement for the Stefan Boltzmann's law. We have said the Stefan Boltzmann's law relates the intensity of radiation with the temperature of the black body, and the Wien's law relates the lambda maximum with the temperature of the black body, and the Rayleigh-Jeans law provides a theoretical model using which they have tried to explain the black body radiation. We have seen the Stefan Boltzmann's law statement. Since the radiation intensity is proportional to the fourth power of the temperature of the black body, this law also is called as T power 4 law. We have seen the Stefan's constant. we have discussed the blackbody radiation spectrum to understand the Wien's law. We have seen the statement of Wien's law, and we also seen the Rayleigh-Jeans law and the theoretical model that was used by Rayleigh-Jeans to explain the blackbody radiation. We have said that the Rayleigh-Jeans law is in agreement with the experimental value in the infrared region, while it does not agree with the experimental values in the ultraviolet region, and we have said that that is a contradiction. The contradiction is known as ultraviolet catastrophe, and the Rayleigh-Jeans law hints at the shortcomings of classical theories. Thank you.